Hello everyone, my name is Adarsh Kumar and I am here with a beautiful topic of organic chemistry, that is Sn1 reaction. So we are going to discuss Sn1 reaction of alkyl halide. So without wasting time, let us start with the topic. Okay, so we are going to discuss Sn1 reaction of alkyl halide. Okay, so this is called alkyl halide. So we are going to discuss the reaction over alkyl halide and the reaction name is Sn1 reaction. So what is called Sn1 reaction? So before coming at this Sn1 reaction, let us understand something about the nucleophilic substitution reaction. Because Sn1 itself stands for nucleophilic substitution reaction, which is unimolecular. So what does Sn1 stands for? It stands for unimolecular nucleophilic substitution reaction. Okay, fine. Now let us understand briefly about the nucleophilic substitution reaction. Okay, then we will be discussing about the Sn1 reaction. What is called nucleophilic substitution reaction? So let's say alkyl halide. Okay, this is alkyl halide and this is subjected to react with any nucleophile. You know, this is the symbol of nucleophile. So what is called nucleophile? So nucleophile are those species which are rich in electron, isn't it? So this nucleophile will react with this alkyl halide. So this is nothing but the substrate. Okay, this is substrate and this is nucleophile. So this is reacting with the substrate to give one product, and as we well know, the product is R and this nucleophile. Means this bond Rx bond is replaced by RNU bond. Simply we can say that this X, okay, this X is nothing but leaving group. This leaving group is replaced by the nucleophile, okay, and this is the leaving group X minus. So simply here we can understand that this is the reaction in which nucleophile is substituted over the leaving group. Okay, such type of reaction is known as nucleophilic substitution reaction, and we are particularly focusing on the alkyl halide. Okay, fine. So basically this reaction can go via two ways. The first one which we have written here, that is Sn1 reaction, and the other one is Sn2 reaction. Okay, so two reactions are there which are very famous and which we have to discuss thoroughly. This is Sn1 reaction. So first of all we'll discuss about the Sn1 reaction and then we'll discuss about the Sn2 reaction. So again let me recall you what is the full form, or maybe you can say what does Sn1 stands for. So it stands for unimolecular nucleophilic substitution reaction. Fine. So let us understand the mechanism, the reaction pathway, and how the reaction is proceeding, how the products are forming, all the things we will discuss. What are the factors affecting the Sn1 reactions? Okay. So let us understand each and every step in detail. Fine. See, let's say I am taking an example of alkyl halide. So this is the carbon which is attached by a alkyl group. Let's say this is R, fine. And I am taking a bond on dash position, dash bond, which is below the plane. Let's say this is hydrogen, and above the plane, let's say this is deuterium, D. And this is nothing but any X group. Okay, X can be what? Chlorine, bromine, iodine. Sorry, this is iodine. Fine. So this alkyl halide is subjected to react with any nucleophile. Fine. Let's say this is nucleophile. I am representing the nucleophile with Nu minus. Okay. In the same way we have discussed here, this is going to react over the alkyl halide and we are going to get the product. So let us discuss the steps. What are the things involved in the reactions? Okay. The first step is the removal of leaving group. This X is nothing but leaving group which will leave in the reaction. Okay, so this is leaving group which is leaving. Okay, so this is the first step. This in the first step leaving group is leaving. Fine. So let us understand it how it is leaving. So let's say this is the alkyl halide. Fine, and this is the bond above the plane. What I'm trying to say, this bond is cleaving. Fine. So this is the X, del negative, del positive. Well, we can understand this. This bond is breaking, so del positive charge will be accumulated over the carbon and del negative charge will be there on the halogen. Okay, fine. X. This is nothing but a transition state which I am representing by TS1. Okay, this is the transition state first. Definitely, if I am writing it here 1, transition state 2 will also come, right? So let us stand it very clearly. So this bond is cleaving, right? Fine. So this step is the slowest step. Let's say this is step number 1. So step number 1 is the slow step. Why I'm writing a slow step, we'll understand it later. So there is a very good role of this step. Fine. So this is the slow step, and this step is also known as rate determining step. Okay. What is meant by rate determining step? What is why I'm writing it slow step? And slow step is the only rate determining step. Why it is so? We'll understand it. Don't worry. So now, after the first step, this is the leaving group. Okay, after the first step, what is forming? An intermediate is forming. This is the transition state. Just after the transition state, one intermediate is forming. So this intermediate is nothing but what? Sorry, this is dash. So this intermediate is nothing but carbocationic intermediate. Fine. This is a carbocationic intermediate. Fine. And this intermediate, here I am just writing it, this intermediate may rearrange. So we all know the meaning of rearrangement of carbocation. Okay. If you don't know, don't worry. I will be discussing all the things here. Okay, fine. So what can I say? This may rearrange. Fine. Carbocation may rearrange. This intermediate can rearrange itself. Fine. Then we are moving ahead towards the product formation. So before the formation of transition step, one TS was there. So just after the formation of what transition state, one more TS will be there, and I am writing it as TS2. So what is happening in TS2? Simply nucleophile is approaching this carbocation which is formed, okay, for a short period of time. So this nucleophile is attacking over the carbocation in a fast step. This is the point we have to note. This was the slow step and this is the fast step. In the fast step, nucleophile is attacking over the carbocation. Fine. So what about the transition state? Here one transition state would be generated, that would be like carbon, this is alkyl group, this is your hydrogen, this is your deuterium. Okay, fine. And this bond is forming between the nucleophile and the carbocation. Okay, this is the transition state 2, isn't it? And this transition state 2 is formed just after the formation of intermediate in a very fast step, or maybe simply we can say fast step. And then we are getting product. Okay, we are getting products. Now you just say me how many products we can obtain. See, what is the meaning of carbocation? Carbocation simply means this is nothing but sp2 hybridized. Okay, the hybridization of this carbon is nothing but sp2. So this is planar. Moreover, we can say this is trigonal planar. So simply we can represent it like, let's say this is the plane. Okay, this is the plane. I am represented. So this is coming towards us. Fine. Are you able to visualize it? Okay. So this is the carbon and this is your alkyl group. This is hydrogen and this is deuterium. Fine. So if this is planar, don't you think that nucleophile can attack over the carbocation from both the sides, up the plane or maybe simply above the plane and below the plane, isn't it? Above the plane and below the plane. So we will be getting two products, first one plus second one. Fine. We'll be getting two products, first one and second one. One product when nucleophile is attacking above the plane, and the second one would be like nucleophile will be attacking below the plane. Right. These are the two products. And here only I would like to say that both the products are equally what? They are equal in concentration. Why I'm saying like this? Because the probability of nucleophile to attack above the plane and below the plane are equal. So that's why we are getting the product in equal amount. Hence, we are saying that they are racemic mixtures. Racemic mixtures. Okay. So have a look at this page very carefully. These are the basic things which we have to understand. Let me just briefly explain once again. Here this is the bond, CX bond. CX bond is breaking, living group is living, then what is forming? Living group is living in a very slow step. Okay, this is the slow step. Then carbocation is generated. Then again nucleophile is attacking over the carbocation from above the plane and from the below plane. Okay, so we are getting the racemic mixture as the product. Fine. Now let us understand some more thing about the Sn1 reaction. Okay, so is there any doubt in this space? I think no. Fine, let us go ahead. Fine. Now what we have to understand, see, let us understand few points which are very important to be discussed over here. Fine, that I am writing as, oh sorry, what happened? Okay, so let us write as key points. What are the key points which are important to understand in the Sn1 reaction? Okay, the first key point is formation of or maybe like this we can write living group leaves in a slow step. Okay, I am highlighting this. Living group lives in a slow step. Fine. Hence, it is a rate determining step. This is the first point. Second, carbocationic intermediate is formed. Carbocationic intermediate is formed. Fine. Which may what? Rearrange. Fine. Okay, we have discussed it earlier. Third point, what we have discussed is nucleophile attacks the intermediate in a fast step. Sorry, in a fast step. Hence, it will not affect the rate of the reaction. Okay, of the reaction. Fine. So let us understand the meaning of this slow step and why this slow step is the rate determining step of the reaction. So this is somewhat related to kinetics of the reaction. Okay, fine. So why is only slow step is the rate determining step? Okay, let us understand this. So for clearing this concept, I will take one example. Let's say this is a pipe. Okay, this is a narrow pipe, and this is a cross section which is very wide. Fine. And this is the source of water. From here water is flowing in the narrow pipe, and then it is entering in the this bigger pipe, and we are collecting water over here. Let's say this is pipe number 1, this is pipe number 2. Okay, so don't you think that this pipe is only responsible for the rate, because this pipe is only going to take time, isn't it? Because this is not affecting, this pipe is not affecting the rate, the movement of water, because this is narrow. Okay, this is narrow, this is not narrow. So water is coming from point, let's say this is point A, this is point B, and this is point C. So water is coming from point A to point B, taking some time. But if water is coming from point B to point C, it is not taking time. So that's why we can say that this here this narrow pipe is taking some time, and hence rate is only affected by this pipe only. Okay, this is not taking any time, by the way. So maybe it is taking time, but that is negligible as compared to this one. Fine. So we can simply say that rate is what? Rate is that is dependent on the movement of water in this tank, or maybe in this pipe. Fine. So simply we can say that those reactions or those steps which are slow will only decide the rate of the reaction. Hence we can say that this slow step is the rate determining step. Fine. Is it clear to you? Okay. Now second point is carbocationic intermediate is formed which may rearrange. This must be very clear to you. Okay, isn't it? This must be very clear to you. Third thing, nucleophile attacks the intermediate in a fast step, as we have noticed there. No? Nucleophile attacks the intermediate in the very fast step. जो न्यूक्लियोफाइल आपका है बहुत फास्ट स्टेप में अटैक कर रहा है, सो दैट विल नॉट अफेक्ट द रेट ऑफ द रिएक्शन. दिस इज द थर्ड पॉइंट which I would like to mention it here. The fourth point is somewhat related to rate. So after discussing 3 points, we can write the rate expression of the SN1 reaction. So basically, rate is directly proportional to the concentration of alkyl halide only, because this was the first step was the slowest step, and in the first step alkyl halide concentration was only taken, right? So rate is proportional to the concentration of alkyl halide to the power 1. Fine. So we can say that rate is equal to K into concentration of Rx, isn't it? So this is the rate expression. This is what? This is the rate expression. This is the rate expression of SN1 reaction. Fine. Now, from this rate expression, we can say that the order of the reaction is what? 1. So order is what? Order is nothing but the coefficient which is raised over the concentration. So the coefficient which is raised over the concentration is 1. So hence the order is 1. And what about the molecularity? So molecularity is also 1. So that's why we are saying it as unimolecular. Okay. So how the molecularity is also 1? What is the difference of molecularity? So molecularity is nothing but the number of moles of reactants involved in the very slow step. Okay, the number of moles of reactants involved in the very slow step, and the number of moles involved is only 1. That's why the molecularity is 1. Fine. Okay, so let us move ahead and let us discuss few more thing about this in one reaction. Basically this is a good topic, so we have to discuss each and every aspect of SN1 reaction. So let us understand few more things. Okay. See, now the point is, I think the point was in the key point I was discussing about point 4. So let us discuss about point 5, that is potential energy versus potential energy versus reaction coordinate graph. Reaction coordinate graph. Okay. So potential energy versus reaction coordinate graph, I would like to discuss over here. So what was happening? Let us understand this. So this was the alkyl halide. So carbon. This was the alkyl halide. Then nucleophile was attacking over the alkyl halide. So this was R. This was hydrogen. This was deuterium. Right. So nucleophile is attacking over the alkyl halide, and followed so intermediate is formed right now. So here I'm writing it like R H D carbocation. Then basically this is the TS1 as we can recall it. This is TS2, and this is the product. So I'm writing the product as R, and this is the nucleophile D. This is hydrogen plus the inverted product, that would be like, okay, so this is nothing but racemic mixture. racemic mixture. Fine. So let us understand the potential energy versus reaction coordination graph. Sorry, reaction coordinate graph. Here on the y-axis, I am taking potential energy. On the x-axis, I am taking reaction coordinate. Fine. And the graph looks like this. Fine. So this is point number A, this is point number B, this is point number C, this is point number D, and this is point number E. What is point number A? Point number A is simply that point at which reactants are reacting. Okay, so this is alkyl halide CX plus nucleophile. Okay, point number B is nothing but transition state 1. Point number C is nothing but intermediate, carbocationic intermediate. Point number D is transition state 2, and point number E is the product. Fine. So as we can see that intermediate is surrounded by two transition state. Fine. And the energy of intermediate is less than the energy of transition state. Okay, what does this mean? See, the reaction in the reaction coordinate, in the potential energy and reaction coordinate graph, as we can see that the energy of intermediate is less, means this intermediate is more stable than transition state 1 and transition state 2. This intermediate is more what stable than TS1 and TS2. Is it fine? So is there any difficulty in understanding this topic, potential energy versus reaction coordinate graph? Fine. Is it clear? So this reaction is feasible. As we can see that energy of point A was less, but the energy of product is even more less than the reactant. Right. So this reaction is feasible. Fine. So rest of the things we can discuss in the kinetics. So no worry about that. So let us move ahead and let us discuss few more things about the Sn1 reaction. Okay. So what are the things we are going to discuss further? That is about the Sn1 reaction. Before that, I would like to give one example how we can interpret the graph of potential energy versus reaction coordinate for any example. Let's say one example I am writing it here. Let's say this is CS3, CS3, CS2, and this is iodine. This is reacting over water. So here water is the nucleophile. So we will get one product, basically two products. Okay, we'll get two products. So what would be the versus reaction coordinate graph? Coordinate graph. Fine. So we have to draw potential energy versus reaction coordinate graph. Let us draw it. This will clarify the concept of potential energy versus reaction coordinate. So in the first step, what is happening? let's say I'm just drawing it with the bond line representation. Fine, is it fine for you? So this is two bonds, ch3 ch3, this is ch, this is ch2, and this is I. Fine. So this is the leaving group which is living in the very first step, that is the slowest step, isn't it? This is the carbocation. So this is nothing but the intermediate. So before that we can imagine one transition state should be there. Fine. So just after the formation of transition state, we had noted one more point, that is this carbocation may rearrange if it is possible. So here, as we can see that this is the primary carbocation, right? So this may rearrange because next to this carbon, tertiary carbon is there. So on the tertiary carbon, this carbocation may rearrange. So how it can rearrange? So this can rearrange by hydride shift, isn't it? So this hydrogen would be shifted over here, and this carbocation will be coming. This cation will be coming over the carbon. So this will be the picture. Okay. So what we are going to discuss? See, this was the intermediate. So I am naming this intermediate as I1. Okay. So this was the transition state 1. So after the intermediate formation, so this is the transition state 2. This is nothing but the transition state only. Okay, because carbocation is rearranging itself. So this is nothing but the transition state 2. Just after the formation of transition state 2, one more intermediate would be formed. So this is the new intermediate, which is stable one. Fine, this is the stable intermediate. And just after the formation of intermediate, nucleophile will attack over the intermediate. Okay, and this can attack above the plane and below the plane. So two products will be formed. Before that, before the product formation, I would like to mention one more thing, that here transition state 3 is also formed. Okay, so here what we are noticing, that uh, if let's say this is the what it called intermediate, so beside each intermediate, two transition states are there. See, this was the intermediate, right? So beside this transition state, ts3 is there, ts2 is there. This was also an intermediate, isn't it? So beside this intermediate, two ts should be there, ts1 and ts2. So if you are forming any intermediate, so beside that, two transition states should be there. Now look at the product. What would be the product? Product would be, okay, then after removal of H plus, then we'll get tertiary alcohol. Fine. So what about the reaction coordinate? I'm writing it here. Fine. This is potential energy. This is progress of reaction, or simply reaction coordinate. Okay, this is point number A. Transition state 2, point number B. Intermediate, point number C. Transition state 2, that is rearrangement, point number D. Then just after the transition state 2, intermediate is formed, that is more stable than the first intermediate, that is point number E. Then again transition state 3, point number F. Then finally we are getting product. Point number G. How many points? That is C. A, B, this is A, this is B, transition state 1. Then after that intermediate is formed, that is point number C. Point number D is also formed, this is point number D. Point number E is transition state that is formed, which is more stable. This is point number F, sorry. And this is point number G. So I think this picture must have cleared all the things about potential energy and reaction coordinate graph. Okay. Now few more things I would like to discuss in this particular session. Okay. So what are the factors which all affect the Sn1 reaction? Okay. The next topic is factors affecting Sn1 reaction. Okay. The first factor which I am going to discuss over here is nature of substrate. Okay, nature of substrate. So what do you think? What should be the nature of substrate? So as we have seen that carbocation is formed, and those carbocation which is more stable will be preferred over the carbocation which is less stable, simply. So what do you think? 3-degree carbocation is more stable or 2-degree? Simply 3 degrees more stable because of hyperconjugation, as you well know that. Okay, so I'll take a few examples and we will understand it, how the nature of substrate is affecting the Sn1 reaction. Fine. So let us take few examples. The first example which I am going to take is based on degree of the alkyl halide. Let's see. So out of 3, which substrate is more favorable towards Sn1 reaction? What do you think? First, this is first one, this is second one, this is third one. Okay, so this is producing a stable carbocation, isn't it? So this will be more stable than this one, than this one. Let us go ahead, discuss few more. See, okay, this is first example. What do you think? Which alkyl halide is more feasible towards SN1 reaction? 1 or 2? 1. Why? The carbocation which is formed after the removal of leaving group is on the benzylic position, and as we well know that benzylic position is more stable because this benzylic position can show resonance. This is not the benzylic position, that's why this alkyl halide is more reactive. Fine. Third one, let me give a few more examples. So this is X. What do you think? Which carbocation generated will be more stable? So basically See, here X is there, which is on the bridgehead position, isn't it? And this is not the bridgehead position. The carbocation generated over the bridgehead position are not stable. Okay, so this carbocation is not stable. This carbocation is stable. Fine. So this will give better Sn1 reaction. Fine. Point number, question number 4. So let's say this is oxygen and this is alkyl halide. Sorry, this is any living group maybe. Okay, or maybe you can write iodine, X equal to iodine here. Second case. Which one is more stable? The carbocation generated over this carbon is more stable, or this one? What do you think? The carbocation generated over this cation, this carbon will be more stable, isn't it? Because here electron can be donated by the oxygen, plus M effect is observed here over here. So that's why the rate of reaction will be more for fourth. Oh, sorry, this first substrate. Fine. Fifth example. See, I'm writing it here. This is very good example, so try to solve this. Lots of people used to confuse in this example. So which alkyl halide will give better Sn1 reaction? Are you thinking of plus I effect? No. Hyperconjugation is dominated over the plus I effect. So first think about the hyperconjugation. So see how many alpha hydrogens are there. After the formation of carbocation, we'll see the alpha hydrogens. Okay. So here we have 4 alpha hydrogens. And here we have how many alpha hydrogens? 5 alpha hydrogens. So simply this alkyl halide is more reactive towards the Sn1 reaction. Okay, so I am talking about the alpha hydrogens just after the removal of this leaving group. Positive charge would be generated over here, and then hence we can count the alpha H, which is 4 in this case, and in this case which is 5. So hence this alkyl halide is more favorable towards the Sn1 reaction. So thanks for today. This is all about the Sn1 reaction in the today's session. So we'll be discussing about the Sn1 reaction in the further session, rest of the things, and thank you so much.